Welcome back to the course Basics of Mechanical Engineering 3. We are discussing about the thermodynamics and fluid mechanics in this course. The first part was thermodynamics, where I took tutorial sessions and took VLab sessions, demonstration of the laboratory, that is virtual laboratory demonstrations were there. I have talked about the fluid mechanics introduction in the first tutorial of fluid mechanics in the previous tutorial. Now I will talk about some more concepts of fluid mechanics in this tutorial that are discussed already in the lecture series. I am Dr. Amandeep Singh Oberoi from IIT Kanpur. Pascal's law, as it was discussed, which says P is equal to F by A, simply pressure is equal to force by area. Pascal's law states that the pressure is applied to an enclosed fluid, it is transmitted undiminished to all points of fluid to the walls of its container. This principle allows a small force applied at one piston to be converted into larger force at another piston when the area is increased. Because pressure is inversely proportional to area, that is what they say, the force could be converted from one size or one surface to another surface. For instance, if it is a force that is applied on a piston, you can see this is a large area. In a smaller area, this force is applied. This pressure is exerted all towards the walls. Pressure inside the liquid, and this is the area A based upon which this pressure is exerted upon, and this force is F. You can see some weight is there, is showing the weight of the elephant. Based upon this force and this area, this pressure is exerted. So this is Pascal's law. Directly I am come to a problem statement. Area of piston M and N is 0.06 meter square and 0.17 meter square respectively. If a 50 Newton force is applied on M, what will be the force on the piston N? Now in this case, if I try to draw this, it is something like this. We have two pistons, that is M and N. There is one piston like this, in which force is applied, that is M. Is another piston in which again the force is applied, that is N. These pistons have forces applied upon, and we have a system something like this. Force comes from M, force comes from N, and this pressure from M and N turns out to be a total pressure here. Now this is a piston, I would say. Here the force that is given is 50 Newton for M, 50 Newton of force they say, and for N we need to find what is the force value. Area of the piston for M, it is given as A is equal to 0.06 meter square, and area for N is given as 0.17 meter square. Now given values, I will call this as area 1, that is for M, and area 2, that is for N. We have A1, A2 as 0.06 meter square and 0.17 meter square. We have F1 as 50 Newton, F2 is to be calculated. Now we know Pascal's law say M is equal to pressure on piston N. So when we say as per Pascal's law, pressure on piston N, that is equal to pressure on piston N, which means F1 by A1 is equal to F2 by A2, putting the values 50 by 0.06 is equal to F2 by 0.17. This gives me the value of F2 as 141.7 newtons. Very simple problem. Now let me try to see a similar problem when 3 piston setups are there. Force acting on X and Y is given by 225 Newton and 200 Newton respectively. Find the force acting on Z. They have been given with this figure. There is piston 1, there is piston 2, and there is a third piston. They say X, Y, Z, 3 pistons are there. These are connected to the forces here. This is X, this is Y, this is Z. For X they say it is 225 Newton of force. For Y they say it is 200 Newton of force acting here. And for Z, what is the force we need to calculate. And also they say find the force acting on Z given the piston X and Z is of area 30 centimeter square and 5 centimeter square respectively. So this area is given here. Area for piston X is 30 centimeter square and for the piston Z is 5 centimeter square. It is very simple problem statement. Once again, we have been given force on X, force on Y, and force on Z is to be calculated. Force on X is 225 newtons, force on Y is 200 newtons, and we have also been given area of X and area of Z. Area of Y piston is to be calculated. For X and Z, the area is 30 centimeter square and 5 centimeter square respectively. For Y, we need to find it out. So according to Pascal law, we will say as per Pascal's law, since the pressure is constant, P on X is equal to P on Y is equal to P on Z. Therefore, force X by area X is equal to force Y by area Y is equal to force Z by area Z. Putting the values, 225 by 30 is equal to 200 by area Y. This is equal to force Z by area of Z, that is 5. Now, if I call this as 1, that is for X, for Y I call it as 2, Z I call this ratio as 3. When I compare 1 and 2, I will say 1 versus 2, that is 225 by 30 is equal to 200 by area of Y. This gives me area of Y as 26.67 centimeter square. Please note that I am putting here centimeter square only because in the question also it was given centimeter square area, did not convert into meters because we are talking about ratios. In the ratios, the areas are cancelled all the time. It is always a ratio, so that doesn't matter at all. Now this area is calculated, and when I compare 2 and 3, now in 2 we can put this as 200 by 26.67, that is Fy by Ay. This is equal to Fz by 5. I got the value of Fz here as 5 into 200 by 26.67, Fg comes out as 37.5 Newton. This was very simple problems on Pascal law, and these are generally very important because when we talk about fluids, the pressure and exerted on one piston and second piston, pressure is always constant. This is the concept that we wanted to talk about here. Now I will talk about Bernoulli's theorem. Bernoulli's theorem, to recall the concept, it states that for an incompressible frictionless fluid, the total mechanical energy, that is pressure energy, kinetic energy and potential energy along a streamline remains constant. That is, we have pressure head, we have kinetic energy head, we have potential energy head. This stays constant. This is also discussed in detail in the lectures. I will only come to the problem statement. You can see here area is given, V1, P1 is given and H1 is there on one end, and the other end also area is A2, velocity is V2 and P2 is the pressure, and height, that is the head difference here, is H2. In this case they say P is static pressure, rho is fluid density, V is flow velocity of fluid, G is gravity, that is acceleration due to gravity, H is elevation above a reference level. So they say this stays constant. That means in this case P1 plus half rho V1 square plus rho G H1 would be equal to P2 plus half rho V2 square plus rho G H2. This is also mentioned here in the next slide. The pipe and the height difference, P1 plus rho G H1 plus half rho V1 square, that is, we have pressure head, we have potential energy head, we have kinetic energy head. This is equal to the total sum of these heads, and this is always a constant. That is what is Bernoulli theorem states. When to use, the pipe or flow path has different points at different elevations, that is, height matters. In the horizontal pipe there is no change in height, that is, H is 0. When H tends 0, this potential head is 0, that is, no potential energy, that is, height is 0. Then we have half rho V1 square plus P1 is equal to half rho V2 square plus P2. This is constant. So when to use this concept, when the fluid is moving through a pipe or channel where both the points are at same height, there is no change in elevation, that is, there is no change in elevation. So let me try to see in problem statement here. In this problem statement, it says calculate the minimum pressure required to force the blood from the heart to the top of head vertical distance of 0.5 meter. Assume the density of blood to be 1040 kilograms per meter cube, and friction is also to be neglected here. Here it says the pressure difference, that is the head difference, is 0.5 meter. That is, we have given H1 minus H2 as 0.5 meter. That is, for instance, I have a heart here and I have head here. From here they say there is a distance of 0.5 meter and blood is flowing, right, for which rho is given as 1040 kg per meter cube. Now we have rho as 1040 kg per meter cube. Now they say calculate the minimum pressure required to force the blood. P1 minus P2, if we say minimum pressure required is P1 minus P2, that is the difference. This is to be calculated. Now we can just put P1 plus rho G H1 plus half rho V1 square is equal to P2 plus rho G H2 plus half rho V2 square. This gives me P1 minus P2 is equal to rho g into H1 minus H2 and half rho V1 square minus V2 square. Now I take V1 is equal to V2, there is no change in velocity, it goes in a constant velocity. This simply gives me P1 minus P2 is equal to rho g H1 minus H2, and we know H1 minus H2 is 0.5, rho is also there 1040, g value we can put, so rho is 1040, g is 9.81 and H1 minus H2 is 0.5. This gives me the pressure difference as 5.101 into 10 raised to power 3 newtons per meter square. So this is the pressure required from this level, I call it as 1, and to this level I call it as 2. It is from heart to brain. Another problem I will take where I will take no height, that is height or H1 is equal to H2. If water enters a horizontal pipe of non-uniform cross-sectional velocity of 0.5 meters per second and leaves the other end with a velocity of 0.3 meters per second. The pressure at first end is 1500 newtons per meter square. Calculate the pressure of water at the other end. Density of water to be taken as 1000 kilograms per meter cube. They say water enters at one end and leaves at other end. It says it is a horizontal pipe, which means H1 is equal to H2. Therefore, no potential energy. It is a pipe, they say a horizontal pipe, in which water enters at one end and leaves at another end. Here there is a pressure difference, they say this pressure, entry pressure here is P is equal to 1500 newtons per meter square. The exit pressure is to be calculated, call it as P2, that is to be calculated. Velocity is given, V1 is 0.5 meters per second, that is entry velocity, and exit velocity V2 is 0.3 meters per second. Given all these values, we have water flowing here and density of water is 1000 kg per meter cube. So we have rho as 1000 kg per meter cube. We have P1, P2 values. P1 is 1500 newtons per meter square. P2 is to be calculated. Velocity, entry and exit are given. Entry velocity is 0.5 meters per second. Exit velocity is 0.3 meters per second. Now, putting this relation without having the potential head, we have P1 plus half rho V1 square is equal to P2 plus half rho V2 square. This means P2 is equal to P1 plus half rho V1 square minus V2 square. This is equal to pressure 1, that is P1, that is given is 1500 newtons per meter square plus half rho is 1000 V1 square minus V2 square. V1 is 0.5 and V2 is 0.3. This pressure is calculated as 1580 newtons per meter square. So that means the question asks calculate the pressure of water at other end. So we have calculated this pressure P2, this is calculated as 1580 newtons per meter square. You can see what we are trying to learn from here is the density is constant here, rho is constant 1000 kilograms per meter cube for water, and sum of two heads, it is the kinetic energy head and pressure head is constant. Now when kinetic energy is decreased, that is velocity is decreased, velocity at V1 was 0.5 and V2 velocity was 0.3. It is understood when velocity is decreased, because it is to be balanced, the pressure would rise. That is to be learnt from here. When pressure was 1500, pressure is increased, that is P2 is greater than P1 because V2 is less than V1. This is what is being balanced here. It is what Bernoulli's theorem is. We have talked about Bernoulli's theorem, like you have seen the concept of Bernoulli's theorem in the real life. Why do a person tends to fall towards the train when the train is just running very fast through them? Because there is a pressure difference, and because of the lower pressure the person falls that. Why do two ships which floating together, if they come together, they will tend to strike each other because of the pressure difference there. Pressure difference, pressure lowers and they could strike each other. This is what is Bernoulli's theorem concept is. Now let me talk about laminar and turbulent flow. This is very important here. The flow has to be either streamlined in certain cases, it has to be turbulent in other cases, and this could be controlled. To control this, there are numbers that we have discussed like Reynolds number, Prandtl number, those are all discussed in the previous lectures. I will take this into numerical statements. Laminar flow is one when fluid particles moves along a very well defined smooth paths or layers with little or no mixing between adjacent layers. This is a laminar flow, you can say. It is going very smooth, there is no mixing or very little mixing between the adjacent layers. It is orderly and characterized by parallel streamlines. Turbulent flow, when there is a turbulence, that is a type of fluid flow in which fluid undergoes irregular fluctuations, that is lot of fluctuation is happening around the fluid. You can see the lines here. If you put a particle here, for example, this particle will just flow and it will just reach in this line itself. In the turbulent flow, if you put a particle here, this particle might even keep on fluctuating and might even go in a different irregular path. The motion of fluid particles is chaotic and eddies from throughout the flow. Now there is a Reynolds number related to laminar flow. Reynolds number is what? To determine whether the flow is laminar or turbulent, we need to calculate the Reynolds number, that is Re. Re is a dimensionless quantity that predicts flow regime in a pipe or channel. Re is equal to rho Vd by mu, where rho is fluid density, V is mean flow velocity, D is diameter of pipe, and mu is dynamic viscosity of the fluid. Now here value of Reynolds number on flow conditions less than 2000 Reynolds number is laminar, more than 4000 Reynolds number is turbulent, and between 2000 and 4000 it is transitional flow, transition between laminar and turbulent. And in open channel these values are different, that is less than 500 it is laminar, more than 1000 it is turbulent, and between these 500 and 1000 it is transition. Now let me take a problem statement here. A fluid with a density of 1000 kilograms per meter cube, that is we are talking about water, is flowing through a pipe with a diameter of 0.5 meter at a velocity of 2 meters per second. The fluid has a viscosity of 0.001 Pascal second. Determine whether the flow is laminar flow or turbulent flow. So they say there is a pipe through which water flows. It says it has viscosity of, that is mu here is 0.001 Pascal seconds, and there is a fluid flowing through this pipe at a velocity of 2 meters per second, and density of the fluid is also given. Rho is 1000 kilograms per meter cube. Diameter of the pipe is also given. The diameter of the pipe is 0.05 meters. Now, for the values of which are all given, we have rho is equal to 1000 kg per meter cube. We have V as 2 meters per second. The diameter of the pipe, which is capital D, is 0.05 meters. The values are completely direct here. So, we have also value of mu, that is 0.001 Pascal second. Putting into the relation to find the Reynolds number, and using the Reynolds number, we will try to see whether it comes less than 2000, it is more than 4000, or it is a transitional, that is between these two values, that is 2000 and 4000. So, Re is rho V T by mu. This is equal to 1000 into 2 into 0.05 by mu, that is 0.001. This value turns out to be 100,000, that is very large number here. That is, it is a highly turbulent flow. This is what it was asked, whether the flow is laminar or turbulent. It is a turbulent flow and highly turbulent. Now, another problem statement in the similar fashion, it says air which has density of 1.225 kilograms per meter cube flows through a pipe of diameter 0.2 meter at a velocity of 0.147 meters per second. The viscosity of air is this. Determine whether the flow is laminar or turbulent. This is a very similar problem statement in which it says it flows through a pipe where air is there. Now, it says we need to find whether the flow is laminar or turbulent, provided the density of fluid, that is air, is 1.225 kilograms per meter cube. The viscosity value, that is mu, is given as 1.81 into 10 raised to power minus 5 Pascal seconds. And we have velocity here, that is it is going in the speed of 0.147 meters per second, that is V, and the diameter of pipe is also given, which is 0.2 meters. Now, the values are given here. We have rho, that is 1.225 kg per meter cube. Then we have V, that is 0.147 meters per second. We have diameter of the tube, that is 0.2 meters, and we also have the viscosity, that is mu, as 1.81 into 10 raised to power minus 5 Pascals second. Now, this is a very similar problem statement, exactly simple formula like this you will put here. You will find the Reynolds number value while putting all these value. R is equal to rho V T by mu, and you will put all the values and try to find it out. The value turns out to be 1989.77, which is less than 2000. Therefore, it is a laminar flow. This value you can put here and try to calculate. I have given you the answer. Last topic in this tutorial is about the vortex. Vortex mechanism is one that refers to the motion of the fluid swirling rapidly around a center, creating a typical type of whirl. This is a whirl that is being created. Now, how do we find the parameters of this whirl? It is a whirl or circular flow when an open tank of liquid is rotated. The liquid's free surface forms a shape called paraboloid due to the outward centrifugal force resulting in a parabolic surface. And here Z is rise of water surface from the center of the edge, which is calculated as omega square r square by 2g. Here omega is angular velocity, r is radius at which the depth is calculated, and g is acceleration due to gravity, that is 9.81 meters per second square. Now we are trying to rotate the liquid. When we try to rotate the liquid, angular velocity omega will come into play. And to find the value of z, that is the rise of the water surface from the center of the edge due to the whirl, we need to find the vortex here. Let me try to see a simple problem statement here. The problem statement here says an open circular tank of 20 centimeter diameter and 100 centimeter length contains water up to a height of 60 centimeter. The tank is rotated above its vertical axis at the rotation speed of 300 rotations per minute. Find the depth of parabola formed at the free surface of water. It says this is an open circular tank. So let me draw this tank. It is an open tank. It says 20 centimeter dia. This dia is 20 centimeter and height is 5 times of dia. That is why I have made a long tank here. And it says it contains water up to 60 centimeter height. This is something like this. Around 60% of the height has water. This is water here. Right? Now, let me put the dimensions first. This is 20 centimeters. This height is 100 centimeters and up to 60 centimeters. It has water. Now, they say the parabola formed when this water tank is rotated, it is rotated above its vertical axis at 300 rpm, right? That is, it is rotated here. This is the vertical axis of the tank if we draw, and this tank is rotated here, and this rotation is 300 rotations per minute. Now, here we will have a whirl. I will try to find the vortex here with a little darker color. I will say it will be something like this, and here this kind of whirl is created like it is shown in this figure. This kind of whirl is created. They say find the depth of parabola. To what point is this whirl going down? To what point it is going down? This depth of parabola we need to find. This depth of parabola, let me say till whatever point, I will call this depth as z. This is to be found. Now, let me put all the values which are given. We have been given d, that is diameter, as 20 centimeters here. You can see in the relation we have omega square r square by 2g. Dia is 20 centimeter, that means the radius would be 10 centimeters. R is equal to d by 2, that is 20 by 2 is equal to 10 centimeters. I will put everything in centimeters only and try to find this value also in centimeters, the value of z. Now, we have length of cylinder L as 100 centimeter, height till which water is there is 60 centimeters. The rotation speed n here is 300 rotations per minute RPM. These are all the values given. Now, what is z? It is omega square r square by 2g. R is given. We need to find omega first. Omega is angular velocity. I will call it as angular velocity. Angular velocity omega is equal to 2 pi n by 60, because rotations per minute I am converting this into seconds. This becomes 2 pi into n is 300 by 60. This turns out to be 31.41 radians per second. Now, to find the depth of parabola, this relation would be used. I will say depth of, I am putting parabola here because I am trying to talk about the one dimension, only depth. Anyway, it is a paraboloid as it is mentioned here. It makes a paraboloid kind of a contour here. So, parabola depth is z, which is equal to omega square r square by 2g. Putting the values here, omega is calculated as 31.41 square into 10 square by 2 into 9.81. This value turns out to be 50.25 centimeters. That means the value of z here that is calculated is 50.25 centimeters. With this, my lecture is closed here. In this tutorial, I talked about certain concepts of fluid mechanics. I talked about Pascal's law. I talked about Bernoulli's theorem. I talked about the vortex, turbulent and laminar flow. I will talk about more concepts of the fluid mechanics in the coming tutorial. Thank you.